Basic Chemistry, Chapter 2, page 24. Many shortcuts in anatomy and physiology lack the time to consider chemistry as a topic. So why do we include it here? The answer is simple. The food you eat, the medicines you take when you are ill, are composed of chemicals. Indeed, your entire body is made up of chemicals, thousands of them, continuously interacting with one another at an incredible pace. It is possible to study anatomy without referencing much to chemistry, but chemical reactions underlie all body processes: movement, digestion, the pumping of your heart, even your thoughts. In this chapter, we present the basics of chemistry and biochemistry, which is the chemistry of living material, providing the background you will need to understand body functions. Headline: Concepts of matter and energy. Differentiate matter from energy. List 4 major energy forms and provide one example of how each energy form is used in the body. Section: Matter. Matter is the stuff of the universe. With some exceptions, it can be seen, smelled, and felt. More precisely, matter is anything that occupies space and has mass, or weight. Chemistry studies the nature of matter, how its building blocks are put together, and how they interact. Matter exists in solid, liquid, and gaseous states. Examples of each state are found in the human body. Solids, such as bones and teeth, have a definite shape and volume. Liquids have a definite volume, but they conform to the shape of their container. Examples of body liquids are blood plasma, the interstitial fluid that bathes all body cells. Gases have neither a definite shape nor a definite volume. The air we breathe is a mixture of gases. Matter may be changed both physically and chemically. Physical changes do not alter the basic nature of a substance. Examples include changes in state, such as ice melting to become water and food being cut into smaller pieces. Chemical changes do alter the composition of the substance, often substantially. Fermenting grapes to make wine and the digestion of food in the body are examples of chemical changes. Heading: Energy. In contrast to matter, energy has no mass and does not take up space. It can be measured only by its effects on matter. We commonly define energy as the ability to do work or to put matter into motion. When energy is actually doing work, or moving objects, we refer it to as kinetic energy. Kinetic energy is displayed in the constant movement of the tiniest particles of matter, which are atoms, as well as in larger objects, such as a bouncing ball. When energy is inactive or stored, as in the batteries of an unused toy, we call it potential energy. All forms of energy exhibit both kinetic and potential work capacities. Actually, energy is a physics topic, but it is difficult to separate matter and energy. All living things are built of matter, and to grow and function they require a continuous supply of energy. Thus, matter is the substance, and the energy is the mover of the substance. Because this is so, let's take a brief detour to introduce the forms of energy the body uses as it does its work. Heading: Forms of energy. Chemical energy. Chemical energy is stored in the bonds of chemical substances. When the bonds are broken, the potential stored energy is unleashed and becomes kinetic energy, energy in action. For example, when gasoline molecules are broken apart in your automobile engine, the energy released powers your car. In like manner, the chemical energy harvested from foods we eat runs all body activities. Heading: Electrical energy. Electrical energy results from the movement of charged particles. In your house, electrical energy is the flow of electrons along the wiring. In your body, an electrical current is generated when charged particles, called ions, move across cell membranes. The nervous system uses electrical currents, called nerve impulses, to transmit messages from one part of the body to another. Heading: Mechanical energy. Mechanical energy is directly involved in moving matter. When you ride a bicycle, your legs provide the mechanical energy that moves the pedals. We can take this example one step further back. As the muscles in your leg shorten, they pull on your bones, causing your limbs to move so that you can pedal the bike. Heading: Radiant energy. Radiant energy travels in waves. That is, it is the energy of the electromagnetic spectrum, which includes X-rays, infrared radiation, heat energy, visible light, radio and ultraviolet waves. Light energy, which stimulates the retinas of your eyes, is important in vision. Ultraviolet waves cause sunburn, but they also stimulate our minds to make vitamin D. Heading: Energy form conversions. With a few exceptions, energy is easily converted from one form to another. For example, chemical energy from gasoline that powers the motor of a speedboat is converted into mechanical energy of the whirling propeller that allows the boat to skim across the water. In the body, chemical energy of foods is trapped in the bonds of high energy chemical called ATP, adenosine triphosphate. And ATP's energy may ultimately be transformed into electrical energy of a nerve impulse or mechanical energy of shortening muscles. Energy conversions are not very efficient, and some of the initial energy supply is always lost to the environment as heat or thermal energy. It is not really lost because energy cannot be created or destroyed, but the part given off as heat is unusable. You can easily demonstrate this principle by touching a light bulb that has been lit for an hour or so. Notice that some of the electrical energy reaching the bulb is producing heat instead of light. Likewise, all energy conversions in the body liberate heat. This heat makes us warm-blooded animals and contributes to our relatively high body temperature, which has an important influence on body functioning. For example, when matter is heated, its particles begin to move more quickly. That is, their kinetic energy of motion, increases. This is important to the chemical reactions that occur in the body because up to a point, the higher the temperature, the faster those reactions occur. We will learn more about this later. Did you get it? Number 1, matter and energy. How are they interrelated? 2. What form of energy is used to transmit messages from one part of the body to another? 3. What type of energy is available when we are still? When we are exercising? Number 4. What does it mean when we say that some energy is lost every time energy changes from one form to another in the body? Heading: Compositions of Matter, page 26. Elements and atoms. Define chemical element and list 4 elements that form the bulk of the body matter. Explain how elements and atoms are related. All matter is composed of a limited number of substances called elements. Unique substances that cannot be broken down into simpler substances by ordinary chemical methods. Examples of elements include many commonly known substances such as oxygen, carbon, gold, copper, and iron. So far, 118 elements have been identified with certainty. 92 of these occur in nature. The rest are made artificially in accelerator devices. 4 elements, carbon, oxygen, hydrogen, and nitrogen, make up 96% of the body weight. Besides these 4 elements, several others are present in small or trace amounts. A complete list of the elements appear in the periodic table, an odd-shaped checkerboard, see Appendix B, that appears in chemistry class rooms all over the world over. The most abundant elements found in the body and their major roles are listed in Table 2.1. Each element is comprised of more or less identical particles or building blocks called atoms. Because all elements are unique, the atoms of each element differ from those of all other elements. We designate each element by 1 or 2-letter chemical shorthand called atomic symbol. In most cases, the atomic symbol is simply the first 2 letters of the element name. For example, C stands for carbon, O for oxygen, Ca for calcium. In a few cases, the atomic symbol is taken from the Latin name of the element. For instance, sodium is indicated by Na from the Latin word natrium. Heading: Atomic Structure, Section 2.5. List these subatomic particles and describe their relative masses, charges, and positions in the atom. The basic atomic subparticles. The word atom comes from the Greek word meaning incapable of being divided. And historically, this idea of an atom was accepted as a scientific truth. According to this notion, you could theoretically divide a pure element, such as a block of gold, into smaller and smaller particles until you got down to the individual atoms, at which point you could subdivide no further. We now know that atoms, although indescribably small, are clusters of even smaller particles called protons, neutrons, and electrons, and that even those subatomic particles can be subdivided with high technology tools. Even so, the old idea of atomic indivisibility is still very useful, because an atom loses the unique properties of its element when it is split into subparticles. An atom's subatomic particles differ in their mass, electrical charge, and position within the atom. Protons, noted as with a P with a tiny plus, have a positive charge, whereas neutrons, N with a 0 above it, are uncharged or neutral. Protons and neutrons are heavy particles and have approximately the same mass, 1 atomic mass, or 1 AMU. The tiny electrons, noted with the E with a minus sign, bear a negative charge equal in strength to the positive charge of the protons, but their mass is so small that it is usually designated as 0 AMU. The electrical charge of a particle is a measure of its ability to attract or repel other charged particles. Particles with the same type of charge, a positive to a positive or a negative to a negative, repel each other, but particles with unlike charges, a positive to a negative, attract each other. Neutral particles are neither attracted to nor repelled by charged particles. Because all atoms are electrically neutral, the number of protons an atom must be precisely matched by its number of electrons. The positive and negative charges will then cancel the effect of each other. Thus, hydrogen has 1 proton and 1 electron, and iron has 26 protons and 26 electrons. For any atom, the number of protons and electrons is always equal. Atoms that have gained or lost electrons are called ions, as we discuss shortly. Going back to the table 2.1 on page 27, common elements making up the human body. Oxygen, atomic symbol is O, percentage of body mass is 65. A major component of both organic and inorganic molecules, as a gas essential to the oxidation of glucose and other food fuels, during which cellular energy, ATP, is produced. Carbon, noted with a C, percentage of body mass 18.5. The primary element in all organic molecules, including carbohydrates, lipids, proteins, and nucleic acids. Element hydrogen, noted with an H, is 9.5% of the body mass, a component of most organic molecules. As an ion, a charged atom, it influences the pH of body fluids. Element nitrogen, noted with an N, is 3.2% of the body mass, a component of proteins and nucleic acids, which are also genetic material. Everything else after is less than 3.9%. Calcium, noted with the Ca, is 1.5% of body mass, found as a salt in bones and teeth, in ionic form, required for muscle contraction, neural transmission, and blood clotting. Phosphorus, noted with a P, is 1% of the body mass, present as a salt in combination with calcium in bones and in teeth. Also present in nucleic acids and many proteins, forms part of the high-energy compound ATP. Potassium, noted with a K, is 0.4% of the body mass. In its ionic form, the major intercellular cation, C-A-T-I-O-N, necessary for the conduction of nerve impulses and for muscle contraction. Sulfur, noted with an S, is 0.3%, a component of proteins, particularly contractile proteins of the muscle. Sodium, noted with that Na, is 0.2%. As an ion, the major extracellular cation, important for water balance, conduction of nerve impulses, and muscle contraction. Chlorine, noted with a Cl, 0.2%. In ionic chloride form, the most abundant extracellular anion, anion. Magnesium, noted with the Mg, 0.1%, present in bone, also an important cofactor for enzyme activity in a number of metabolic reactions. Iodine, noted with an I, 0.1% of body mass, needed to make functional thyroid hormones. Iron, noted with an Fe, 0.1% of body mass, a component of functional hemoglobin molecule, which transports oxygen within red blood cells, and some enzymes. There are some other trace elements, less than 0.01%, chromium with a Cr, cobalt with a Co, copper with a Cu, fluorine with an F, manganese with a Mn, molybdenum, molybdenum, noted with an Mo, selenium with an Se, silicon with an Si, tin with a Sn, vanadium with a V, and zinc with a Zn. Table 2.2, subatomic particles. Protons are found in the nucleus, and it has 1 AMUs, and the charge is positive. Neutrons are in the nucleus. It has 1 AMUs, and it has a 0 or neutral charge. The electron orbits outside of the nucleus, and its mass is 1/2000th, and it has a negative charge. Going on to the next heading, Planetary and Orbit Models of an Atom, page 28. The planetary model of an atom portrays the atom as a miniature solar system, in which the protons and neutrons are clustered at the center of the atom in the atomic nucleus. Because the nucleus contains all heavy particles, it is fantastically dense and positively charged. The tiny electrons orbit around the nucleus in fixed general circular orbits like planets around the sun. But we can never determine the exact location of electrons at a particular time because they jump around following unknown paths. So instead of speaking of specific orbs, chemists talk about orbitals, regions around the nucleus in which a given electron or electron pair is likely to be found most of the time. This more modern model of atomic structure, called the orbital model, has proven to be more useful in predicting the chemical behavior of atoms. The orbit model depicts the general location of electrons outside the nucleus as a haze of negative charge referred to as the electron cloud. Regions where electrons are most likely to be found are shown by denser shading rather than orbit lines. Regardless of the model used, notice that the electrons have the run of nearly the entire volume of the atom. Electrons also determine an atom's chemical behavior, that is, its ability to bond with other atoms. Though now considered outdated, the planetary model is simple and easy to understand and use. Most of the descriptions of atomic structure in this text use that model. Hydrogen is the simplest atom, with just 1 proton and 1 electron. You can visualize the hydrogen atom by imagining it as a sphere with its diameter equal to the length of a football field. The nucleus could then be represented by a lead ball the size of a gumdrop in the exact center of the sphere, and the lone electron pictured as a fly buzzing about unpredictably within the sphere. This mental picture should remind you that most of the volume of an atom is empty space, and most of the mass is in the central nucleus. Did you get it? Question number 5. Which 4 elements make up the bulk of living matter? Question 6. How is an atom related to an element? Heading: Identifying elements. Define radioisotope and describe briefly how radioisotopes are used in diagnosing and treating disease. All protons are alike, regardless of the atom being considered. The same is true of all neutrons and all electrons. So what determines the unique properties of each element? The answer is that the atoms of different elements are composed of different numbers of protons, neutrons, and electrons. The simplest and smallest atom, hydrogen, has one proton, one electron, and no neutrons. Next is the helium atom, with 2 protons, 2 neutrons, and 2 orbiting electrons. Lithium follows with 3 protons, 4 neutrons, and 3 electrons. If we continue this step-by-step listing of subatomic particles, we could describe all known atoms by taking 1 proton and 1 electron at each step. The number of neutrons is not as easy to pin down, but light atoms tend to have equal numbers of protons and neutrons, whereas in larger atoms, neutrons outnumber protons. However, all we really need to know to identify a particular element is its atomic number, mass number, and atomic weight. Taken together, these indicators provide a fairly complete picture of each element. Heading: Atomic number. Each element is given a number called its atomic number that is equal to the number of protons its atoms contain. Atoms of each element contain a different number of protons from the atoms of any other element. Hence, its atomic number is unique. Because the number of protons is always equal to the number of electrons, atomic number indirectly also tells us the number of electrons that atoms contain. Atomic mass. The atomic mass of any atom is the sum of the masses of all the protons and neutrons contained in its nucleus. The mass of the electrons is so small that we ignore it. Hydrogen has 1 bare proton and no neutrons in its nucleus, so its atomic number and atomic mass are the same, 1. Helium, with 2 protons and 2 neutrons, has a mass of 4. The atomic mass number is written as a superscript to the left of the atomic symbol. See examples in figure 2.3, page 30. So for hydrogen, it has this tiny 1 and then a capital H. And that is 1 proton, 0 neutrons, and 1 electrons. Tritium, which is noted with a superscript 3 and a big H, meaning 1 proton, 2 neutrons, and 1 electron. Heading: Atomic weight in isotopes, figure or page 29. At first glance, it seems the atomic weight of an atom should equal its atomic mass. This would be so if there were only one type of atom representing each element. However, the atoms of almost all elements exhibit 2 or more structural variations, and these varieties are called isotopes. Isotopes have the same number of protons and electrons but vary in the number of neutrons they contain. Thus, the isotopes of an element have the same atomic number but different atomic masses. Because all of an element's isotopes have the same number of electrons, and electrons determining bonding properties, their chemical properties are exactly the same. As a general rule, the atomic weight of any element is approximately equal to the mass number of its most abundant isotope. For example, as we said before, hydrogen has an atomic number of 1, but it also has isotopes with atomic masses of 1, 2, 3. And that was referred to earlier, tritium. I was wondering what that was, because it had like H for the hydrogen in there. 1, 2, 3. Its atomic weight is 1.0079, which reveals that its lightest isotope is present in much greater amounts in our world than its 2H or 3H forms. The atomic numbers, mass numbers, and atomic weights for elements commonly found in the body are provided in Table 2.3. And this is on page 30. The heavier isotopes of certain atoms are unstable and tend to decompose to become more stable. Such isotopes are called radioisotopes. The why of this process is very complex, but apparently the glue that holds the atomic nuclei together is weaker in the heavier isotopes. This process of spontaneous atomic decay is called radioactivity and can be compared to a tiny explosion. All types of radioactive decay involve the ejection of particles, alpha or beta, or electromagnetic energy, gamma rays, from the atom's nucleus and are damaging to living cells. Alpha emission has the least penetrating power, gamma radiation the most. Contrary to what some believe, ionizing radiation does not damage the atoms in its path directly. Instead, it sends electrons flying like bowling ball through pins along its path. It is these electrons that do the damage. Radioisotopes are used in minute amounts to tag biological molecules so that they can be followed or traced through the body and are valuable for medical diagnosis and treatment. For example, PET scans, which use radioisotopes, are discussed in a closer look, page 10 through 11. Additionally, a radioisotope of iodine can be used to scan the thyroid gland of a patient suspected of having a thyroid tumor. Radium, cobalt, and certain other radioisotopes are used to destroy localized cancer. Did you get it? Question number 7. An atom has 5 neutrons, 4 protons, and 4 electrons. What is the atomic number? What is its atomic mass? Question number 8. What name is given to an unstable atom that has either more or fewer neutrons than its typical number? And I will now be turning to a closer look, page 10 through 11, on the PET scan. A closer look, medical imaging illuminating the body. Until about 50 years ago, the magical but murky X-ray was the only means of peering into a living body. Produced by directing electromagnetic waves of very short wavelengths at the body, an X-ray is a shadowy negative image of internal structures. What X-rays did and still do best is to visualize hard, bony structures and locate abnormally dense structures like tumors and tuberculosis nodules in the lungs. By bombarding the body with energy, new scanning techniques reveal the structure of internal organs and wring out information about the private and until now secret workings of their molecules. The new imaging techniques are changing the face of medical diagnosis. The 1950s saw the birth of nuclear medicine, which uses radioisotopes to scan the body, and ultrasound techniques. In the 1970s, CT, PET, and MRI scanning techniques were introduced. The best known of these newer imaging devices is computed tomography, CT scans, formerly Computerized Axial Tomography, or CAT, a refined version of X-ray. A CT scanner confines its beam to a thin slice of the body about as thick as a dime, and ends the confusion resulting from images of overlapping structures seen in the conventional X-rays. As a patient is slowly moved through the donut-shaped CT machine, its X-ray tube rotates around the body. Different tissues absorb the radiation in varying amounts, and the device's computer translates this information into detailed cross-sectional picture of the body region scanned. CT scans are at the forefront in evaluating most problems that affect the brain and abdomen, and their clarity has all but eliminated exploratory surgery. Special ultrafast CT scanners have produced a technique called dynamic spatial reconstruction, which provides a three-dimensional images of body organs from any angle. It also allows their movement and changes in their internal volume to be observed at normal speed, in slow motion, and at a specific moment in time. The greatest value of DSR, which is dynamic spatial reconstruction, has been to visualize the heart beating and blood flowing through the blood vessels. This allows medical personnel to assess heart defects, constricted blood vessels, and the status of coronary bypass grafts. Another computer-assisted X-ray technique is digital subtraction angiography, DSA. Angiography is the same as equals vessel pictures. This technique provides an unobstructed view of small arteries. Conventional radiographs are taken before and after a contrast medium is injected into an artery, and then the computer subtracts the before and after image, eliminating all traces of body structures that obscure the vessel. DSA is often used to identify blockages in the arteries that supply the heart wall and the brain. Just as the X-ray spawned new technologies, so did nuclear medicine in the form of the Positron emission tomography, PET scan. PET excels in observing metabolic processes. After receiving an injection of short-lived radioisotopes that have been tagged to biological molecules such as glucose, the patient is positioned in the PET scanner. As the radioisotopes are absorbed by the most active brain cells, high-energy gamma rays are produced. The computer analyzes the gamma emissions and produces a picture of the brain's biochemical activity in vivid colors. PET's greatest clinical value has been its ability to provide insight into brain activity in people affected by mental illness, Alzheimer's disease, and epilepsy. Currently, PET can reveal signs of trouble in those with undiagnosed Alzheimer's disease because regions of beta amyloid accumulation, a defining characteristic of AD, show up in brilliant red and yellow, as in the photo. PET scans can also help predict who may develop AD in the future. Ultrasound imaging, or ultrasonography, has some distinct advantages over the approaches described so far. The equipment is inexpensive and it employs high-frequency sound waves, ultrasound, as its energy source. Ultrasound, unlike ionizing forms of radiation, has no harmful effects on living tissue as far as we know. The body is probed with pulses of sound waves which causes echoes when reflected and scattered by the body tissues. The echoes are analyzed by computer to construct visual images of body organs of interest. Because of its safety, ultrasound is the imaging technique of choice for obstetrics. OBSTETRICS. That is for determining fetal age and position and locating the placenta. Because sound waves have very low penetrating power and are rapidly scattered in the air, sonography is of little value for looking at air-filled structures like the lungs or those surrounded by bone like the brain and the spinal cord. Another technique that depends on non-ionizing radiation is magnetic resonance imaging, MRIs, which uses magnetic fields of up to 60,000 times stronger than Earth's to pry information from the body's tissues. The patient lies in a chamber with a huge magnet. Hydrogen molecules spin like tops in the magnetic field, and their energy is enhanced by radio waves. When the radio waves are turned off, the energy is released and translated by a computer into a visual image. MRI is immensely popular because it can do many things a CT scan cannot. Dense structures do not show up in the MRI, so bones of the skull or the vertebral column do not impair the view of soft tissues such as the brain. MRI is also particularly good at detecting degenerative disease of various kinds. Multiple sclerosis plaques, for example, do not show up well in CT scans but are dazzlingly clear in MRI. A variation of MRI called magnetic resonance spectroscopy, MRS, maps the distribution of elements other than hydrogen to reveal more about how disease changes body chemistry. In 1992, MRI technology leaped forward with the development of the functional MRI, which allows tracking of blood flow into the brain in real time. Until then, matching thoughts, deeds, and disease to corresponding brain activity had been the sole domain of PET. Because a functional MRI does not require injections of tracer elements, it provides another, perhaps more desirable alternative. Despite its advantages, the powerful clanging magnets of the MRI present some thorny problems. For example, they can suck metal objects, such as implanted pacemakers and loose tooth fillings, through the body. Also, there is no convincing evidence that magnetic fields are risk-free. As you can see, modern medical science has made some remarkable diagnostic tools at its disposal. CT and PET scans account for 25% of all imaging. Ultrasonography, because of its safety and low cost, is the most widespread of the new techniques. Conventional X-rays still remain the workhorse of diagnostic imaging techniques and still account for more than half of all imaging currently done. Heading: Molecules and Compounds. Define molecule and explain how molecules are related to compounds. When two or more atoms combine chemically, molecules are formed. If two or more atoms of the same element bond together, a molecule of that element is produced. For example, when two hydrogen atoms bond, a molecule of hydrogen gas is formed. That is H plus H equals H subscript 2. In this example, the reactants, the atoms taking part in the reaction, are indicated by their atomic symbols, and the product, the molecule formed, is indicated by a molecular formula that shows its atomic makeup. The chemical reaction is shown by writing a chemical equation. When two or more different atoms bind together to form a molecule, the molecule is more specifically referred to as a molecule of a compound. For example, 4 hydrogen atoms and 1 carbon can interact chemically to form methane, which is 4H plus C equals CH subscript 4, which is methane. Notice that when numbers of atoms is written as a subscript, it indicates that the atoms are joined by a chemical bond. Thus, 2H is 2 unjoined atoms, but H subscript 2 indicates the 2 hydrogen atoms are bonded together to form a molecule. Thus, a molecule of methane is a compound, but a molecule of hydrogen gas is not. It is called molecular hydrogen. It is important to understand that compounds always have properties quite different from those of the atoms making them up, and it would be next to impossible to determine the atoms making up a compound without analyzing it chemically. Sodium chloride is an excellent example of the difference in properties between a compound and its constituent atoms. Sodium is a silvery white metal, and chlorine, in its molecular state, is a poisonous green gas used to make bleach. However, sodium chloride is table salt, a white crystalline solid that we sprinkle on our food. Notice that just an atom is the smallest particle of an element that still retains that element's property. A molecule is the smallest particle of a compound that still retains the properties of that compound. Let me read that again. Notice that just as an atom is the smallest particle of an atom that still retains that element's property, a molecule is the smallest particle of a compound that still retains the properties of that compound. If you break the bonds between the atoms of the compound, properties of the atoms rather than those of the compound will be exhibited. Did you get it? Question number 9. What is the meaning of the term molecule? Question number 10. How does a molecule of an element differ from the molecule of a compound? Heading, page 32, Chemical Bonds and Chemical Reactions. Recognize that chemical reactions involve the interaction of electrons to make and break chemical bonds. Differentiate ionic polar covalent and non-polar covalent bonds and describe the importance of hydrogen bonds. Contrast synthesis, decomposition, and exchange reactions. Chemical reactions occur whenever atoms combine with or dissociate from other atoms. When atoms unite chemically, chemical bonds are formed. Heading Bond Formation. It is important to understand that a chemical bond is not an actual physical structure like a pair of handcuffs linking two people together. Instead, it is an energy relationship that involves interactions between the electrons of the reacting atoms. Because this is so, let's consider the role of electrons play in forming bonds. Role of electrons. Electrons occupy orbits or generally fixed regions of the space around the nucleus. These regions are called electron shells or energy levels. The maximum number of electron shells in any atom known so far is 7, and these are numbered 1 through 7 from the nucleus outwards. The electrons closest to the nucleus are those most strongly attracted to its positive charge, and those farther away are less securely held. As a result, the more distant electrons are likely to interact with other atoms. Perhaps this situation can be compared to the development of a child. During infancy and the toddler years, the child spends most of its time at home and is shaped and modeled by the ideas and demands of its parents. However, when the child goes to school, it is increasingly influenced by friends and other adults, such as teachers and coaches. Thus, just as a child is more likely to become involved with the outsiders as it roams farther from home, electrons are more influenced by other atoms as they get farther and farther away from the positive influence of the nucleus. There is an upper limit to the number of electrons that each electron shell can hold. Shell number 1, closest to the nucleus, is small and can accommodate only 2 electrons. Shell 2 holds a maximum of 8. Shell 3 can accommodate up to 18. Subsequent shells hold larger and larger number of electrons. In most, but not all cases, the shells tend to be filled consecutively. The only electrons that are important when considering bonding behavior are those in the atom's outermost shell. This shell is called the valence shell, and its electrons determine the chemical behavior of the atom. As a general rule, the electrons of the inner shells do not take part in bonding. When the valence shell of an atom contains 8 electrons, the atom is completely stable and is chemically inactive or inert. When the valence shell contains fewer than 8 electrons, an atom will tend to gain, lose, or share electrons with other atoms to reach a stable state. When any of these events occur, chemical bonds are formed. Examples of chemically inert and reactive elements are shown in Figure 2.5. So, chemically inert elements, helium is next to neon. We'll have to look at that. Is on page 33, Figure 2.5. The key to chemical reactivity is referred to the rule of 8s. That is, atoms interact in such a way that they will have 8 electrons in their valence shell. The first electron shell represents an exception to this rule because it is full when it has 2 electrons. As you might guess, atoms must approach each other very closely for their electrons to interact. In fact, their outermost electrons shells must overlap. Heading: Types of chemical bonds. Ionic bonds form when electrons are completely transferred from one atom to another. Atoms are electrically neutral, but when they gain or lose electron during bonding, their positive and negative charges are no longer balanced and charged particles called ions result. When an atom gains an electron, it acquires a net negative charge because it now has more electrons than protons. Negatively charged ions are more specifically called anions. When an atom loses an electron, it becomes positively charged ion, a cation. because it now possesses more protons than electrons. It may help you to remember that a cation is a positively charged ion by thinking of its T as a plus sign. Both anions and cations result when an ionic form is formed. Because opposite charges attract, the newly created ions tend to stay close together. The formation of sodium chloride, NaCl, common table salt, provides a good example of ionic bonding. Sodium's valence shell contains only one electron and is incomplete. However, if this single electron is lost to another atom, shell 2, which contains 8 electrons, becomes the valence shell. Thus, sodium becomes a cation and achieves stability. Chlorine needs only one electron to fill its valence shell, and it is much easier to gain one electron, forming chloride with a minus, than to give away 7. Thus, the ideal situation for sodium to donate its valence shell electron to chlorine. And this is exactly what happens in the interaction between these two atoms. Sodium chloride and most other compounds formed by ionic bonding fall into the general category of chemicals called salts. Heading: Covalent Bonds. Electrons do not have to be completely lost or gained for atoms to become stable. Instead, they can be shared in such a way that each atom is able to fill its valence shell at least part of the time. Molecules in which atoms share electrons are called covalent molecules, and their bonds are covalent bonds. CO means with, and valent means having power, so covalent bonds. So with power, they're bonds with power. For example, hydrogen with its single electron can become stable if it fills its valence shell by sharing a pair of electrons it owns and one from another atom. A hydrogen atom can share an electron pair with another hydrogen atom to form a molecule of hydrogen gas. This is shown in figure 2.7a. This would be a great time to look at the pictures on page 34 and 35. It'd be a lot less confusing than listening to these words. But anyways, the shared electron pair orbits the whole molecule and satisfies the stability needs of both hydrogen atoms. Likewise, two atoms, oxygen atoms, each with 6 valence shell electrons, can pair 2 pairs of electrons and form double bonds with each other to form a molecule of oxygen gas. So like that again, 2 oxygen atoms, each with 6 valence shell electrons, so there's like 2 missing from each valences, can share 2 pairs of electrons with each other to form a molecule of oxygen, O2. So that picture is available on page 35. A hydrogen atom may also share its electron with an atom of a different element. Carbon has 4 valence shell electrons but needs 8 to achieve stability. When methane, CH subscript 4, is formed, carbon shares 4 electron pairs with 4 hydrogen atoms. Because the shared electrons orbit and belong to the whole molecule, each atom has a valence shell enough of the time to satisfy its stability needs. In the covalent molecules described thus far, electrons have been shared equally between the atoms of the molecule. Such molecules are called nonpolar, covalently bonded molecules. However, electrons are not shared equally in all cases. When covalent bonds are made, the molecule formed always has a definite three-dimensional shape. A molecule's shape plays a major role in determining just what other molecules or atoms it can interact with. The shape may also result in unequal electron pair sharing. The following 2 examples illustrate this principle. Carbon dioxide is formed when a carbon atom shares its 4 valence shell electrons with two oxygen atoms. Oxygen is a very electron-hungry atom and attracts the shared electrons much more strongly than does carbon. However, because the carbon dioxide molecule is linear, shown as O equals C equals O, which means more like O covalently bonded with C, I think, I'm not sure. The electron pulling power of one oxygen atom is offset by that of the other, like a tug of war at a standoff between equally strong teams, shown in figure 2.8 on page 36. As a result, the electron pairs are shared equally and orbit the entire molecule, and carbon dioxide is a nonpolar molecule. A water molecule is formed when two hydrogen atoms bind covalently to a single oxygen atom. Each oxygen atom shares an electron pair with the oxygen atom, and again the oxygen has the stronger electron attracting ability, but in this case the molecule formed is bent or V-shaped, and it looks like H with a line to O back to an H. You just got to look at it. It looks like a V. The two hydrogen atoms are located at one end of the molecule, and the oxygen atom is at the other, figure 2.8b. Consequently, the electron pairs are not shared equally. This arrangement allows them to spend more time in the vicinity of the hydrogen atom. Because electrons are negatively charged, that end of the molecule becomes more negative, indicated by an 8 minus. It looks like an 8, but it looks like an unfinished 8. So slightly negative is what it's called. Slightly more negative is the sign. And the hydrogen end becomes slightly more positive, indicated by a sort of 8 looking with a plus. In other words, a polar molecule, a molecule with two charged poles, is formed. Polar molecules orient themselves towards other polar molecules or charged particles, ions, proteins, and others. And they play an important role in chemical reactions that occur in body cells. Because body tissues are 60 to 80% water, the fact that water is a polar molecule is particularly significant, as we will describe shortly. Heading: Hydrogen bonds. Hydrogen bonds are extremely weak bonds formed when a hydrogen atom bound to one electron-hungry nitrogen or oxygen atom is attracted by another electron-hungry atom, and the hydrogen atom forms a bridge between them. Hydrogen bonding is common between water molecules, figure 2.9. and is reflected in the water's surface tension. The surface tension of water causes it to ball up or form spears when it sits on a surface, and allows some insects, like water striders, to walk on water as long as they tread lightly. Hydrogen bonds are also important intramolecular bonds. That is, they help to bind different parts of the same molecule together in a special three-dimensional shape. These rather fragile bonds are very important to maintain the structure of protein molecules, which are essential functional molecules and body-building materials. Heading: Patterns of chemical reactions, page 37. Chemical reactions involve the making or breaking of bonds between atoms. The total number of atoms remains the same, but the atoms appear in new combinations. Most chemical reactions have one of three recognizable patterns we will describe next. Synthesis reactions. Synthesis reactions occur when two or more atoms or molecules combine to form a larger, more complex molecule, which can be simply represented as A plus B turns into AB. Synthesis reaction always involve bond formation, because Energy must be absorbed to make bonds. Synthesis reactions are energy bond absorbing reactions. Synthesis reactions underlie all anabolic activities that occur in body cells. They are particularly important for growth and for repair of worn out or damaged tissues. The formation of a protein molecule by joining of amino acid into long chains is a synthesis reaction. Heading: Decomposition Reactions, page 38. Decomposition reactions occur when a molecule is broken down into smaller molecules, atoms, or ions, and can be indicated by AB turns into A plus B. Essentially, decomposition reactions are synthesis reactions in reverse. Bonds are always broken, and the products of these reactions are smaller and simpler than the original molecules. As bonds are broken, chemical energy is released. Decomposition reactions underlie all catabolic or destructive processes that occur in the body. That is, they are molecule-degrading reactions. Examples of decomposition reactions that occur in the body include the digestion of foods into their building blocks and the breakdown of glycogen, a large carbohydrate molecule stored in the liver, to release glucose. Figure 2.10b, when blood levels start to decline. Heading: Exchange reactions. Exchange reactions involve both synthesis and decomposition reactions. Bonds are both made and broken. During exchange reactions, a switch is made between molecule parts, changing partners, so to speak, and different molecules are made. Thus, an exchange reaction can be generally indicated as AB plus C turns into AC plus B, and AB plus CD turns into AD plus CB. An exchange reaction occurs, for example, when ATP reacts with glucose and transfers its end phosphate group to glucose, forming glucose phosphate. Figure 2.10c. At the same time, ATP becomes ADP. This important reaction, which occurs whenever glucose enters a body cell, effectively traps the glucose fuel molecule inside the cell. Regardless of the type of reaction occurring, most chemical reactions are reversible. If chemical bonds can be made, they can be broken, and vice versa. Reversibility is indicated by a double arrow. When arrows differ in length, the longer arrow indicates the more rapid reaction or the major direction in which the reaction is proceeding. For example, in the reaction A plus B equals AB, and the top arrow of the equal sign is actually longer and the bottom one is shorter, the reaction is going to the right is occurring more rapidly. And over time, AB will accumulate while AB will decrease in amount. If the arrows are of equal length, the reaction is at chemical equilibrium. Thus, A plus B equals AB with equal, same length equal signs. You'll have to just look at it on page 38. For each molecule of AB made, a molecule AB is breaking down to release A and B, whatever that means. Heading: Factors influencing the rate of chemical reactions. For atoms and molecules to react chemically, they must collide forcefully, so that the electrons in their valence shells can interact. Bonds making and breaking cannot occur long distance. Several factors influence the kinetic energy and, hence, the speed of the particles and the force of collisions. And that is shown in Table 2.4. Did you get it? How do ionic bonds differ from covalent bonds? Question number 12. What kind of bonds form between water molecules? Question number 13. What reaction type in figure 2.10 occurs when fats are digested in your small intestines? Number 14. Can you indicate a chemical reaction? How can you indicate that a chemical reaction is reversible? Heading page 38, Biochemistry, the chemical composition of living matter. Distinguish organic from inorganic compounds. All chemicals found in the body fall into one of two major classes of molecules. They are either inorganic or organic compounds. The class of compound is determined solely by the presence or absence of carbon, with a few so far unexplainable exceptions, such as carbon dioxide gas and carbon monoxide. Inorganic compounds lack carbon and tend to be small, simple molecules. Examples of inorganic compounds found in the body are water, salts, and many, but not all, acids and bases. Organic compounds are carbon-containing compounds. The important organic compounds in the body are carbohydrates, lipids, proteins, and nucleic acids. All organic compounds are fairly, or very, largely covalently bonded molecules. Inorganic and organic compounds are equally essential for life. Trying to put a price tag on which is more valuable can be compared to trying to decide whether the ignition system or the engine is more essential to the operation of a car. And Table 2.4 on page 39, factors increasing the rate of chemical reactions, as referred to in the factors influencing the rate of chemical reactions on page 38. Increasing temperature, increasing the kinetic energy of molecules, which in turn move more rapidly and collide more forcefully. Increasing the concentration of reacting particles, which increases the number of collisions because increased numbers of reacting particles. Decreasing particle size. Smaller particles have more kinetic energy and move faster than larger ones, hence they take part in more collisions. Presence of catalysts. Decrease the amount of energy the molecules need to interact by holding the reactants in the proper positions to interact. That's see page 51. So that table doesn't really make that much sense. It's kind of vague unless you're interested in chemical reactions or versed in it. Okay, heading on page 39, inorganic compounds. Explain the importance of water to body homeostasis and provide several examples of the roles of water. List several salts or their ions vitally important to body functioning. Differentiate a salt, an acid, and a base. Explain the concept of pH and state the pH of blood. Heading water. Water is the most abundant inorganic compound in the body. It accounts for about 2/3 of the body weight. Among the properties that make water so vital are the following. 1. High heat capacity. Water has a high heat capacity. That is, it absorbs and releases large amounts of heat before its temperature changes appreciably. Thus, it prevents the sudden changes in body temperature that might otherwise result from intense sun exposure, chilling winter winds, or internal events such as vigorous muscle activity that liberate large amounts of heat. Number 2, polarity, solvent properties. Because of its polarity, water is an excellent solvent. Indeed, it is often called the universal solvent. A solvent is a liquid or gas in which smaller amounts of other substances called solutes, which may be gases, liquids, or solids, can be dissolved or suspended. The resulting mixture is called a solution when the solute particles are exceedingly tiny, and a suspension when the solute particles are fairly large. Translucent mixtures with solute particles of intermediate size are called colloids. Small reactive chemicals such as salts, acids, and bases dissolve easily in water and become evenly distributed. Molecules cannot react chemically unless they are in solution, so virtually all chemical reactions that occur in the body depend on water's solvent properties. Because nutrients, respiratory gases, oxygen and carbon dioxide, and wastes can dissolve in water, water can act as a transport and exchange medium in the body. For example, all these substances are carried from one point of the body to another in blood plasma and are exchanged between the blood and the tissue cells by passing through the interstitial fluid. Specialized molecules that lubricate the body, such as mucus, also use water as their solvent, and synovial fluids, oil at the ends of the bones as they move within joint cavities. Number 3, chemical reactivity. Water is an important reactant in some types of chemical reactions. For example, to digest foods or break down biological molecules, water molecules are added to the bonds of the larger molecules. Such reactions are called hydrolysis reactions. Page 40. A term that specifically recognizes this role of water, which is denoted by hydro, which equals water, and lysis, which means splitting. Number 4, cushioning. Water also serves as a protective function in the form of cerebrospinal fluid. Cerebrospinal fluid. Water forms a cushion around the brain that helps to protect it from physical trauma. Amniotic fluid, which surrounds a developing fetus within the mother's body, plays a similar role in protecting the fetus. Heading: salts. A salt is an ionic compound containing cations other than hydrogen plus and anions other than hydroxyl ions, which is OH minus. Salts of many metal elements are commonly found in the body, but the most plentiful salts are those containing calcium and phosphorus, found chiefly in the bones and teeth. When dissolved in body fluids, salts easily separate into their ions. This process, called dissociation, occurs rather easily because the ions have already been formed. All that remains is to pull the ions apart. This is accomplished by polar water molecules, which orient themselves with their slightly negative ends towards the cations and their slightly positive ends towards the anions, and thereby overcome the attraction between them. Salts, both in their ionic forms and in combination with other elements, are vital to body functioning. For example, sodium and potassium ions are essential for nerve impulses, and iron forms part of the hemoglobin molecule that transports oxygen within red blood cells. Because ions are charged particles, all salts are electrolytes, substances that conduct an electrical current in solution. When ionic or electrolyte balance is severely disturbed, virtually nothing in the body works. The functions of the elements found in body salts are summarized in Table 2.1 on page 27. Heading: acid and bases. Like salts, acids and bases are electrolytes, that is, they ionize and then dissociate in water and can then conduct an electrical current. Heading: characteristics of acids. Acids have a sour taste and can dissolve many metals or burn a hole in your rug. Acids can have a devastating effect. For example, consider the damage to sea life, trees, and famous historical monuments caused by vinegar-like acid rain. But most useful definition of an acid is that it is a substance that can release hydrogen ions, which is noted by H+, in detectable amounts. Because a hydrogen ion is essentially a hydrogen nucleus, a naked proton, acids are also defined as proton donors. When acids are dissolved in water, they release hydrogen ions and some anions. The anions are unimportant. It is the release of the protons that determines an acid's effect on the environment. The ionization of hydrochloric acid, an acid produced by stomach cells that aids digestion, is shown in the following equation. HCl, which is hydrochloric acid, turns into H proton plus chlorine anion, so H plus plus C plus minus. You just got to look at it. It's on page 40, bottom. Other acids found or produced in the body include acetic acid, the acid component of vinegar, and carbonic acid. Acids that ionize completely and liberate all their protons are called strong acids. An example is hydrochloric acids. Acids that ionize incompletely, as do acetic or carbonic acid, are called weak acids. For example, when carbonic acid dissolves in water, only some of its molecules ionize to liberate H positive. So 2H carbonic acid, 2H2CO3, turns into, looks like a hydrogen proton, then it turns into HCO3, which is an anion, and there's still some carbonic acid left over. So only some of its molecules ionize to liberate. That is on page 41. Characteristics of bases. Bases have a bitter taste, feel slippery, and are proton acceptors. These hydroxides are common in organic bases. Like acids, the hydroxides ionize and dissociate in water. But in this case, the hydroxyl ion and some cations are released. The ionization of sodium hydroxide, commonly known as Li, is shown as NaOH. Sodium hydroxide turns into Na+, which is a cation, plus OH negative, which is a hydroxyl ion. The hydroxyl ion is an avid proton seeker, and any base containing this ion is considered a strong base. By contrast, bicarbonate ion, an important base in blood, is a fairly weak base. When acids and bases are mixed, they react with each other in exchange reaction to form a water and salt. So hydrochloric acid and sodium hydroxide turn into water and salt. This type of exchange reaction, in which an acid and a base interact, is more specifically called neutralization reactions. Heading: pH, acid-base concentrations. Losing my mind. Page 41. The relative concentration of hydrogen and hydroxyl ions in various body fluids is measured in concentration units called pH units. That is noted with a little p, big H. The idea for a pH scale was devised in 1909 by a Danish biochemist and a part-time beer brewer named Sorensen, and is based on the number of protons in solution expressed in terms of moles per liter. The mole is a concentration unit. Its precise definition need not concern us here. The label 1m at the top right of figure 2.12 on page 42 means 1 mole of sodium hydroxide per liter of solution. The pH scale runs from 0 to 14, and each successive change of 1 pH represents a tenfold change in the hydrogen ion concentration. At a pH of 7, the scale midpoint, the number of hydrogen ions exactly equals the number of hydroxyl ions, and the solution is neutral. That is neither acidic or basic. Acidic or basic. Solutions with a pH lower than 7 are acidic. The hydrogen ions outnumber the hydroxyl ions. A solution with a pH of 6 has 10 times as many hydrogen ions as a solution with a pH of 7, and a pH of 7 indicates a 10,000-fold, 10 times 10 times 10 times 10, increase in hydrogen ion concentration. Solutions with a pH higher than 7 are alkaline or basic, and solutions with a pH of 8 and 12 respectively have 1/10 and 1/100,000th the number of hydrogen ions present in a solution with a pH of 7. So it's just explaining the log of 10 as in relation to the hydrogen ions. Living cells are extraordinarily sensitive to even slight changes in pH, and the acid-base balance is carefully regulated by the kidneys, lungs, and a number of chemicals called buffers, which are present in body fluids. Weak acids and weak bases are important components of the body's buffer system, which act to maintain pH stability by taking up excess hydrogen or hydroxyl ions. Because blood comes into close contact with nearly every body cell, regulation of blood pH is especially critical. Normally, blood pH varies a narrow range from 7.35 to 7.45. When blood pH changes more than a few tenths of a pH unit from these limits, death becomes a distinct possibility. Although we could give hundreds of examples to illustrate this point, we will provide just one very important one. When blood pH begins to dip into the acid range, the amount of life-sustaining oxygen that the hemoglobin in blood carry to blood cells begins to fall rapidly to dangerous low levels. Figure 2.12 shows the approximate pH values of several common substances. Did you get it? What property of water prevents rapid changes in body temperature? Question number 16, page 41. What is a proton donor? An acid or a base? Or which one is a proton donor? 17. Is a pH of 11 acidic or basic? Question number 18. Biochemistry is wet chemistry. What does this statement mean? Number 19. Salts are electrolytes. What does that mean? Turning to page 42, heading Organic Compounds. Explain the role of dehydration synthesis and hydrolysis in formation and breakdown of organic molecules. Compare and contrast carbohydrates and lipids in terms of their building blocks, structures, and functions in the body. Most organic molecules are very large molecules, but their interactions with other molecules typically involve only small reactive parts to their structure called functional groups, acid groups, amines, and others. As you will see shortly, many biological molecules, carbohydrates, and proteins, for example, are polymers. Polymers are chain-like molecules made up of many similar or repeating units called monomers, which are joined together by dehydration synthesis. During dehydration synthesis, a hydrogen atom is removed from one monomer and a hydroxyl group is removed from the monomer it is to be joined with. As a covalent bond unites the monomers, a water molecule is released. This removal of a water molecule at the bond site occurs each time a monomer is added to the growing polymer chain. When polymers must be broken down or digested to their monomers, the reverse process called hydrolysis occurs. As water molecule is added to each bond, the bond is broken, releasing the monomers. Other than the monomers, all organic molecules you will meet in this chapter are formed by dehydration synthesis and broken down by hydrolysis. Heading Carbohydrates. Carbohydrates, which include sugars and starches, contain carbon, hydrogen, and oxygen. With slight variations, the hydrogen and oxygen atoms appear in the same ratio as in water, that is, 2 hydrogen atoms to 1 oxygen atom. This is reflected in the word carbohydrate, which means hydrated carbon. And in the molecular formula of sugars, for example, glucose is C≦6H12O6, and ribose is C5H10O5. By the way, anything ending in OSE, I believe, means sugar of some sort. I'm not sure. Double check. Carbohydrates are classified according to size and solubility in water as monosaccharides, disaccharides, or polysaccharides. Because monosaccharides are joined to form the molecules of the other two groups, they are structural units or building blocks of carbohydrates. Let's learn what monosaccharides are. Monosaccharides, which is the heading, means one sugar. One means mono, or one. Monosaccharides means one sugar, and thus monosaccharides are referred to as simple sugars. Mono means one, sugar is apparently saccharide. They are single chain or single ring structures containing from 3 to 7 carbon atoms. The most important monosaccharide in the body are glucose, fructose, galactose, ribose, and deoxyribose. Glucose, also called blood sugar, is the universal cellular fuel. Fructose and galactose are converted to glucose for use by body cells. Ribose and deoxyribose form part of the structure of nucleic acid, another group of organic molecules. Disaccharides, or double sugars, are formed when two simple sugars are joined by dehydration synthesis. In this reaction, as noted earlier, a water molecule is lost as the bond forms. Some of the important disaccharides in the diet are sucrose, or glucose fructose, which is cane sugar, lactose, glucose galactose, found in milk, and maltose, which is glucose, or malt sugar. Because the double sugars are too large to pass through cell membranes, they must be broken down to their monosaccharides units to be absorbed from the digestive tract into the blood. This is accomplished by hydrolysis. Polysaccharides, long branching chains linked simple sugars, are called polysaccharides, literally meaning many sugars. Because they are large, insoluble molecules, they are ideal storage products. Another consequence of their large size is that they lack the sweetness of simple and double sugars. Only two polysaccharides, starch and glycogen, are major importance to the body. Starch is the storage polysaccharide formed by plants. We ingest it in the form of starchy foods such as grains, grain products, and root vegetables like potatoes and carrots, for example. Glycogen is a slightly smaller but similar polysaccharide found in animal tissues, largely in muscles and the liver. Like starch, it is formed of linked glucose units. Carbohydrates provide a ready, easily used source of food energy for cells, and glucose is at the top of the cellular menu. When glucose is oxidized combined with oxygen in a complex set of chemical reactions, it is broken down into carbon dioxide and water. Some of the energy released as glucose bonds are broken and is trapped in the bonds of high-energy ATP molecules, the energy currency of all body cells. If not immediately needed for ATP synthesis, dietary carbohydrates are converted to glycogen or fat and stored. Those of us who have gained weight from eating too many carbohydrate-rich snacks have first-hand experience of this conversion process! ! Hee hee. Small amounts of carbohydrates are used for structural purposes and represent 1 to 2% of cell mass. Some sugars are found in our genes, and others are attached to the outer surface of cell membranes where they act as road signs to guide cellular interactions. Heading: Lipids. Lipids are a large and diverse group of organic compounds. There's a big table of them on page 45. They enter the body in the form of fat marbled meats, egg yolks, milk products, and oils. The most abundant lipids in the body are triglycerides, phospholipids, and steroids. Like carbohydrates, all lipids contain carbon, hydrogen, and oxygen atoms, but in lipids, carbon and hydrogen atoms far outnumber oxygen atoms, as illustrated by the formula for a typical fat named tristerin, tristearin, C57H110O6. Most lipids are insoluble in water but readily dissolve in other lipids and in organic solvents such as alcohol and acetone. Heading Triglycerides. The triglycerides, or neutral fats, are composed of two types of building blocks, fatty acids and glycerol. Their synthesis involves the attachment of three fatty acids to a single glycerol molecule. The result is an E-shaped molecule that represents the tines of a fork. Page 46, figure 215. Although the glycerol backbone is the same in all neutral fats, the fatty acid chains vary. This variation results in different kinds of neutral fats. The length of the triglycerides fatty acid chains and their type of C carbon-to-carbon bonds determine how solid the molecule is at a given temperature. Fatty acid chains with only single covalent bonds between carbon atoms are referred to as saturated. Their fatty acid chains are straight, and at room temperature the molecules of saturated fat pack closely together, forming a solid. Fatty acids that contain one or more double bonds between carbon atoms are said to be unsaturated, monosaturated, and polysaturated, respectively. The double and triple bonds cause the fatty acid chains to kink so that they cannot pack closely enough to solidify. Hence, triglycerides with short fatty acid chains or unsaturated fatty acids are oils, liquid at room temperature. Plant lipids are typically oils. Examples include olive oil, rich in monounsaturated fats, and soybean and safflower oils, which contain a high percentage of polyunsaturated fatty acids. Longer fatty acid chains and more saturated fatty acids are common in animal fats, such as butterfat and the fat of meats, which are solid at room temperature. Of the two types of fatty acids, the unsaturated variety, especially olive oil, is said to be more heart-healthy. Trans fats, common in many margarines and baked products, are oils that have been solidified by addition of hydrogen atoms at the site of the double carbon bonds. They have recently been branded as increasing the risk of heart disease even more than solid animal fats. In contrast, omega-3 fatty acids found in cold water fish appear to decrease the risk of heart disease and some inflammatory diseases. Triglycerides represent the body's most abundant and concentrated source of usable energy. When they are oxidized, they use large amounts of energy. They are stored chiefly in fat deposits beneath the skin and around the body organs, where they help insulate the body and protect deeper body tissue from heat loss and bumps. Heading Phospholipids. Phospholipids are similar to triglycerides. They differ in that a phosphorus-containing group is always part of the molecule and take place of one of the fatty acid chains. Thus, phospholipids have two instead of three attached fatty acids. Because of the phosphorus-containing portion, the head, bears an electrical charge, it gives phospholipids special chemical properties and polarity. For example, the charged region attracts and interacts with water and ions, but the fatty chains, the tail, do not. And the presence of phospholipids in cellular boundaries in the membranes allows cells to be selective about what may enter or leave. Steroids are basically flat molecules formed of four interlocking rings. See figure 215C. Thus, their structure differs quite a bit from that of fats. However, like fats, steroids are largely made of hydrogen and carbon atoms and are fat soluble. The single most important steroid molecule is cholesterol. We ingest cholesterol in animal products such as meat, eggs, and cheese, and some made by the liver regardless of dietary intake. single most important steroid molecule is cholesterol. Cholesterol has earned bad press because of its role in arteriosclerosis, but is essential for human life. Cholesterol is found in cell membranes and is the raw material of vitamin D, steroid hormones, and bile salts. Although steroid hormones are present in the body in only small quantities, they are vital to homeostasis. Without sex hormones, reproduction would be impossible, and without the corticosteroids produced by the adrenal glands, the body would not survive. Did you get it? What are the structural units or building blocks of carbohydrates? And what are the structural units of lipids? What is the importance of the R group seen here? Just ignore that question unless you want to go to page 48. Question number 21. What type of lipid is abundant in cellular membranes? Question number 22. Is the formation of glycogen from glucose an example of hydrolysis or dehydration synthesis? Heading: Proteins. Differentiate fibrous proteins from globular proteins. Define enzyme and explain the role of enzymes. Proteins account for over 50% of the organic matter in the body, and they have the most varied function of organic molecules. Some are construction materials, others play vital roles in cell function. Like carbohydrates and lipids, all proteins contain carbon, oxygen, and hydrogen. In addition, they contain nitrogen and sometimes sulfur atoms as well. The building blocks of proteins are small molecules called amino acids. About 20 common varieties of amino acids are found in proteins. All amino acids have an amine group, which is NH2, which gives them basic properties, an acid group, which gives them basic properties, and an acid group, COOH, which allows them to act as acids. In fact, all amino acids are identical except for a single group of atoms called their R group, which is on figure 2.17 on page 48. Differences in the R groups make each amino acid chemically unique. For example, an extra acid group, COOH, in the R group makes the amino acid more acidic. Amino acids are joined together in chains to form large, complex protein molecules that contain from 50 to thousands of amino acids. Amino acid chains containing fewer than 50 amino acids are called polypeptides. Because each type of amino acid has distinct properties, the sequence in which they are bound together produces proteins that vary widely both in structure and function. To understand this more easily, think of the 20 amino acids as a 20-letter alphabet. The letters, amino acids, are used in a specific combination to form words. The letters, parentheses, amino acids, are used in specific combinations to form words, a protein. Just as a change in one letter of any word can produce a word with an entirely different meaning, like flower to floor, or one that is nonsensical, like flower to fleur, changes kind of amino acids or letters in their positions in the protein allow literally thousands of different protein molecules to be made. Heading: Structural levels of protein. We can provide proteins in terms of 4 structural levels. The sequence of amino acids comprising the polypeptide chain is the primary structure of a protein. This structure, which resembles a strand of amino acid beads, is the backbone of the protein molecule. Proteins do not normally function as simple linear chains of amino acids. Instead, they twist or bend upon themselves to form a more complex secondary structure. The most common secondary structure is the alpha helix, which resembles a slinky toy or the coils of a telephone cord. The alpha helix is formed by coiling the primary chain and is stabilized by hydrogen bonds. Hydrogen bonds in alpha helix always link different parts of the same chain together. In another type of secondary structure, the beta pleated sheet, the primary polypeptide chains do not coil, but are linked side by hydrogen bonds to form a pleated ribbon-like structure that resembles an accordion. See figure 2.12b. In this secondary structure, the hydrogen bonds may link together different polypeptide chains as well as different parts of the same chain that has folded back on itself. Many proteins have tertiary structure, the higher level of complexity. Tertiary structure is achieved when an alpha helix or a beta pleated region of the polypeptide chain fold upon one another to produce a compact ball-like globular molecule, figure 2.18c. The unique structure is maintained by covalent and hydrogen bonds between amino acids that are often far apart in the primary chain. When two or more polypeptide chains combine in a regular manner to form a complex protein, the protein has a quaternary structure, figure 2.18d. Although a protein with a tertiary or quaternary, Quaternary structure looks a bit like a clump of congealed pasta, the final structure of any protein is very specific and is dictated by its primary structure. In other words, the types and positions of amino acids in the protein backbone determine where the bonds can form to keep water-loving amino acids near the surface and water-fleeing amino acids buried in the protein core. Fibrous and globular proteins. Based on their overall shape and structure, proteins are classified as either fibrous or globular. The strand-like fibrous proteins, also called structural proteins, appear most often in body structures. Some exhibit only secondary structure, but most have tertiary or even quaternary structure. I just looked up quaternary. They are very important in binding structures together and providing strength in certain body tissues. For example, collagen is found in bones, cartilage, and tendons and is the most abundant protein in the body. Keratin is the structural protein of hair and nails and the materials that make skin tough. Globular proteins are mobile, generally compact, spherical molecules that have at least tertiary structure. These water-soluble proteins play crucial roles in virtually all biological processes because they do things rather than just form structures. They are also called functional proteins. The scope of their activities is remarkable. Some antibodies help to provide immunity. Other hormones help to regulate growth and development. Still others, called enzymes, regulate essentially every chemical reaction that goes on within the body. The fibrous structural proteins are exceptionally stable, but the globular functional proteins are quite the opposite. Hydrogen bonds are critically important in maintaining their structure, but hydrogen bonds are fragile and are easily broken by heat and excess of pH. When their three-dimensional structures are destroyed, the proteins are said to be denatured and can no longer perform their physiological roles. Why? Their function depends on their specific structure, most importantly on the presence of particular collections of atoms called active sites on their surface that fit and interact chemically with other molecules of complementary shape and charge. See figure 2.20. Hemoglobin becomes totally unstable to bind and transport oxygen when blood pH becomes too acidic, as we hinted earlier. Pepsin, a protein digesting enzyme that acts in the stomach, is inactivated by alkaline pH. In each case, the improper pH has destroyed the structure needed for function. Except for enzymes, we describe most important types of functional proteins with the organ system or functional process to which they are closely related. For instance, we discuss protein hormones in the endocrine system chapter. chapter 9, hemoglobin in the chapter on blood, chapter 10, and antibodies in the chapter on the lymphatic system and body defenses in chapter 12. However, enzymes are important in the functioning of all body cells, so we consider these incredibly complex molecules here. Heading: Enzymes and Enzyme Activity. Enzymes are functional proteins that act as biological catalysts. A catalyst is a substance that increases the rate of a chemical reaction without becoming part of it or of the product or being changed itself. Enzymes accomplish this feat by binding to and holding the reaction molecules, the substrates, in proper position for chemical interaction. While the substrates are bound to the enzyme's active site, they undergo structural changes that results in a new product. Once the reaction has occurred, enzyme releases the product. Because the enzymes are not changed in doing their job, they are reusable, and the cells need only small amounts of each enzyme. Enzymes are capable of catalyzing millions of reactions each minute. However, they do more than just increase the speed of chemical reactions. They also determine which reactions are possible at a particular time. No enzyme, no reaction. Enzymes can be compared to a bellows used to fan a sluggish fire into flaming activity. Without enzymes, biochemical reactions would occur far too slowly to sustain life. Although there are hundreds of different kinds of enzymes in the body cells, they are very specific in their activities, each controlling only one or a small group of chemical reactions and acting only on specific molecules. Most enzymes are named according to the specific type of reactions they catalyze. There are hydrolases, which add water, oxidases, which causes oxidization, and so on. In most cases, you can recognize an enzyme by the suffix -ase, ase, forming its name. Many enzymes are produced in an inactive form and must be activated in some way before they can function. In other cases, enzymes are inactivated immediately after they have performed their catalytic function. Both events are true of enzymes that promote blood clotting when a blood vessel has been damaged. If this were not so, large numbers of unneeded and potentially lethal blood clots would be formed. Did you get it? Question number 23. What is the primary structure of proteins? 24. Of fibrous and globular proteins, which is more important for body-building structures? 25. How does an enzyme recognize its substrates? Heading: Nucleic Acids. Compare and contrast the structure and functions of DNA and RNA. Explain the importance of ATP in the body. The role of nucleic acids is fundamental. They make up the genes which provide the basic blueprint of life. They not only determine what type of organism you will be, but also direct your growth and development. And they do this largely by dictating protein structure. Remember that enzymes, which catalyze all the chemical reactions that occur in the body, are proteins. Nucleic acids, composed of carbon, oxygen, hydrogen, nitrogen, and phosphorus atoms, are largest biological molecules in the body. Their building blocks, the nucleotides, are quite complex. Each consists of three basic parts: a nitrogen-containing base, a pentose 5-carbon sugar, and a phosphate group. Figure 2.21a and b. The bases come in 5 varieties: adenine, guanine, cytosine, thymine, and uracil. The abbreviations are AGCTU. A and G are large 2-ring bases, whereas the others are small single-ring structures. The nucleotides are named according to the base they contain. A containing bases are adenine nucleotides. C containing bases are cytosine nucleotides, and so on. This part is filled with a lot of pictures, so you would probably want to look at it this whole chapter actually. This is page 52 and 53. The two major kinds of nucleic acids are deoxyribonucleic acid and ribonucleic acid, DNA and RNA. DNA and RNA differ in many aspects. DNA is genetic material found within the cell nucleus. The control center of the cell has two fundamental roles. One, it replicates itself exactly before a cell divides, thus ensuring that the genetic information in every body cell is identical. And it provides the instructions for building every protein in the body. For the most part, RNA is located outside of the nucleus and can be considered the molecular slave of the DNA. That is, RNA carries out the orders for protein synthesis issued by DNA. Although both RNA and DNA are formed by the joining together of nucleotides, their final structures are different. DNA is a long double chain of nucleotides. Its bases are A, G, T, and C, and its sugar is deoxyribose. Its two nucleotide chains are held together by hydrogen bonds between the bases, forming a ladder-like molecule. Alternating sugar and phosphate molecules form the uprights, or the backbones of the ladder, and each rung is formed by two joined bases, one base pair. Binding of the bases is very specific. A always binds to T, and G always binds to C. Thus, A and T are said to be complementary, as are C and G. A base sequence of A, T, G, A on one nucleotide chain would necessarily be bonded to the complementary base sequence T, A, C, T on the other nucleotide strand. The whole molecule is then coiled into a spiral staircase structure called the double helix. Whereas DNA is double-stranded, RNA molecules are single nucleotide strands. The RNA bases are A, G, C, and U. U replaces the T found in DNA, and its sugar is ribose instead of deoxyribose. Three major varieties of RNA exist: messenger, ribosomal, and transfer RNA, and each has a specific role to play in carrying out DNA's instructions for building proteins. Messenger RNA carries the information for building the protein from the DNA genes to the ribosomes and the protein synthesizing sites. Transfer RNA ferries amino acids to the ribosomes. Ribosomal RNA forms part of the ribosomes, where it oversees the translation of the message and the binding together of amino acids to form the protein. We describe protein synthesis in greater detail in Chapter 3. Heading: Adenosine triphosphate ATP. The synthesis of adenosine triphosphate, or ATP, is all important because it provides a form of chemical energy that all body cells can use. Without ATP, molecules cannot be made or broken down, cells cannot maintain their boundaries, and all life processes grind to a halt. Although glucose is the most important fuel for body cells, none of the chemical energy contained in its bonds can be used directly to power cellular work. Instead, energy is released as glucose is catabolized and is captured and stored in the bonds of the ATP molecules as small packets of energy. Structurally, ATP is a modified nucleotide. It consists of an adenosine base, ribosome sugar, and 3 phosphate groups, figure 222a. The phosphate groups are attached by unique chemical bonds called high-energy phosphate bonds. When these bonds are broken by hydrolysis, energy is liberated and can be used immediately by the cell to do work or power a particular activity, such as synthesizing proteins, transporting substances across its membrane, or in the case of muscle cells, contracting, figure 223c. ATP can be compared to a tightly coiled spring that is ready to uncoil with tremendous energy when the catch is released. The consequence of breaking its terminal phosphate bond can be represented as ATP into ADP plus P, which is inorganic phosphate, plus E is energy. This is on bottom of page 55. As ATP is used to provide cellular energy, adenosine diphosphate, ADP, accumulates, and ATP supplies are replenished by oxidation of food fuels. Essentially, the same amount of energy must be captured and used to reattach a phosphate group to ADP. That is, to reverse the reaction as liberated when terminal phosphate is removed from ATP. Did you get it? How do DNA and RNA differ from each other in the kinds of bases and sugars they contain? Question number 27. What is the vital importance of ATP to body cells? Page 56, this is a focus on careers. I think it's just like a little tidbit. It says pharmacy technician. To recognize how medications affect patients, pharmacy technicians need thorough understanding of anatomy and physiology. That means I'm not going to go be a pharm tech. I don't want to do chemistry. When most people get a new medication, they open up a package, toss out the little pamphlet that goes into detail about how the medication works. Not Chris Green. I love reading the package inserts, says Green, the lead pharmacy technician at a CVS drugstore. Farm techs? Really? Maybe a pharmacist, not a farm tech. Green's enthusiasm for those details is a lifesaver for his customers. Pharmacy technicians, or that's what I heard, I'm sorry to be prejudiced. Pharmacy technicians are a vital link in the chain between doctor and patient. Although pharmacy technicians are legally prohibited from talking with patients about their symptoms, they can translate medical jargon and discuss a medication's side effect and other precautions a patient may need to take. For example, doctors may recommend that patients who are on certain medications for a long time have regular tests such as eye exams, blood work, or tests for liver function. A pharmacy technician can convey that information to that patient and check on subsequent visits to make sure he or she is following up. A busy retail pharmacy has various stations: data entry, where the patient's record is updated with a new prescription; production, where the prescription is filled; and verification, where the pharmacist reviews the prescription and makes sure it is filled and labeled correctly. Green's job is to make sure the process flows smoothly from station to station. Green started working as a cashier at a drugstore when he was in high school and gradually became interested in pharmacy itself. I was interested in how drugs work and how they can help people and improve their health, he says. Having earned a bachelor's degree in biology, Green emphasizes that pharmacy techs must have a good grasp of sciences, especially basic chemistry and anatomy and physiology, to help them understand each drug's makeup and properties. When all the data is entered, we see what potential side effects there are. It is important to know how medications work and how they interact with each other and how they interact with the body. I might see something and bring it to the pharmacist's attention. In addition, communication skills and the ability to work with people are important. Good communication skills may be the difference between life and death. Blah, 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 blah. Going on to the summary. Concepts of energy and matter. This is on page 57. 1. Matter. Matter is anything that occupies space and has mass. B. Matter exists in three states: gaseous, liquid, and solid. 2. Energy. Energy is the capacity to do work and to move matter. Energy has kinetic, or active energy, and potential, or stored work capacities. Energy forms that are important in body functions include chemical, electrical, mechanical, and radiant. Energy forms can be converted from one form to another, but some energy is always unusable or lost in heat in such transformations. Compositions of matter. Elements and atoms. Each element is a unique substance that cannot be decomposed into simpler substances by ordinary chemical methods. A total of 118 electrons exist. 118 elements exist. They differ from one another in their chemical and physical properties. 4 elements, carbon, hydrogen, oxygen, and nitrogen, make up 96% of living matter. Several other elements are present in small or trace amounts. The building blocks of elements are atoms. Each atom is designated by an atomic symbol consistent consisting of one or two letters. Atomic structure. Atoms are composed of three subatomic particles, protons, electrons, and neutrons. Because all atoms are electrically neutral, the number of protons in any atom is equal to the number of its protons. The planetary model of an atom portrays all the mass of the atom's protons and neutrons concentrated in a minute central nucleus. Electrons orbit the nucleus along specific orbits. The orbital model also locates protons and neutrons in a central nucleus, but it depicts electrons as occupying space called orbitals and forming an electron cloud of negative charge around the nucleus. Each atom can be identified by atomic number, which is equal to the number of protons contained in the atom's nucleus. The atomic mass number is equal to the sum of the protons and neutrons in the atom's nucleus. Isotopes are different atomic forms of the same element. They differ only in the number of neutrons in the nucleus. Many of the heavier isotopes are unstable and decompose to a more stable form by ejecting particles or energy from the nucleus, a phenomenon called radioactivity. Such radioisotopes are useful in medical diagnosis and treatment and in biochemical research. The atomic weight is approximately equal to the mass number of the most abundant isotope of any element. Molecules and compounds. A molecule is the smallest unit resulting from binding of two or more atoms. If the atoms are different, a molecule of a compound is formed. Compounds exhibit properties different from the atoms they comprise. Chemical bonds and reactions. Bond formation. Chemical bonds are energy relationships. Electrons in the outermost energy level, valence shell, of the reacting atoms are active in bonding. Atoms with a full valence shell, 2 electrons in shell 1 or 8 in the subsequent shells, are chemically inactive. Those with an incomplete valence shell interact by losing, gaining, or sharing electrons to achieve stability, that is, to fill the valence shell. Ions are formed when valence shell electrons are completely transferred from one atom to another. The oppositely charged ion thus formed attract each other, forming an ionic bond. Ionic bonds are common in salts. Covalent bonds involve the sharing of electrons pairs between atoms. If the electrons are shared equally, the molecule is a nonpolar covalent molecule. If the electrons are not shared equally, the molecule is a polar covalent molecule. Polar molecules orient themselves towards charged particles and other molecules. Hydrogen bonds are fragile bonds that bind together water molecules or different parts of the same molecule, intramolecular bonds. They are common in large, complex organic molecules such as proteins and nucleic acids. Patterns of chemical reactions. Chemical reactions involve the formation or breaking of chemical bonds. They are indicated by a chemical equation which provides information about the atomic composition or the formula of the reactants and products. Chemical reactions that result in larger, more complex molecules are synthesis reactions. They involve bond formation. In decomposition reactions, larger molecules are broken down into simpler molecules or atoms. Bonds are broken. Exchange reactions involve both making and the breaking of bonds. Atoms are replaced by other atoms. Regardless of the type of reaction, most chemical reactions are reversible. Reversibility is indicated by a double arrow. Factors increasing the rate of chemical reactions. For atoms to interact chemically, they must collide forcefully. Factors that affect the number or force of collisions include the temperature, concentration of the reactants, particle size, and catalysts. Heading: Biochemistry, page 58. The chemical composition of living matter. Inorganic compounds. Inorganic compounds make up living matter, do not contain carbon except CO2 and CO. They include water, salts, and some acids and bases. Water is the single most abundant compound in the body. It acts as a universal solvent in which electrolytes, salts, acids, and bases ionize and in which chemical reactions occur, and it is the basis of transport and lubricating fluids. It slowly absorbs and releases heat, thus helping to maintain homeostatic body temperature, and it protects certain body structures, such as the brain, by forming a watery cushion. Water is also a reactant in hydrolysis reactions. Salts in ionic forms are involved in nerve transmission, muscle contraction, blood clotting, transport of oxygen by hemoglobin, metabolism, and many other reactions. Additionally, calcium salts, as bone salts, contribute to bone hardness. Acids are proton donors. When dissolved in water, they release hydrogen ions. Strong acids dissociate completely. Weak acids dissociate incompletely. Bases are protein acceptors. The most important inorganic bases are hydroxides. Bicarbonate ions are important bases in the body. When bases and acids interact, neutralization occurs. That is, a salt and water are formed. The relative concentration of hydrogen and hydroxyl ions in various body fluids is measured by a pH scale. Each change of 1 pH unit represents a tenfold change in the hydrogen ion concentration. A pH 7 is neutral. That is, the concentration of hydrogen and hydroxyl ions are equal. A pH below 7 is acidic. A pH above 7 is alkaline. Normal blood range pH ranges from 7.35 to 7.45. Slight deviations outside this range can be fatal. Organic compounds. Organic compounds are the carbon-containing compounds that comprise living matter. Carbohydrates, lipids, proteins, and nucleic acids are examples. They all contain carbon, oxygen, and hydrogen. Proteins and nucleic acids also contain substantial amounts of nitrogen. Carbohydrates contain carbon, hydrogen, and oxygen in the general relationship of 2 hydrogen atoms to 1 atom to 1 carbon atom. Their building blocks are monosaccharides. Monosaccharides includes glucose, fructose, galactose, deoxyribose, and ribose. Disaccharides includes sucrose, maltose, and lactose, and polysaccharides includes starch and glycogen. Carbohydrates are ingested as sugars and starches. Carbohydrates, and in particular glucose, are the major energy source for formation of ATP. Lipids include triglycerides, glycerol plus 3 fatty acid chains, phospholipids, and steroids, the most important of which is cholesterol. Triglycerides, neutral fats, are found primarily in fatty tissue where they provide insulation and reserve body fuel. Phospholipids and cholesterol are found in all cell membranes. Cholesterol also forms the basis of certain hormones, bile salts, and vitamin D. Like carbohydrates, the lipids are degraded by hydrolysis and synthesized by dehydration synthesis. Proteins are constructed from building blocks called amino acids. 20 common types of amino acids are found in the body. Levels of protein structure include the amino acid chain, primary, the alpha helix and beta pleated sheet, secondary, a ball-like structure superimposed on secondary structure, which is tertiary, and a globular structure formed by 2 or more polypeptide chains, quaternary. Amino acid sequence determines the proteins constructed. Fibrous or structural proteins are the basic structural materials of the body. Globular proteins are also called functional proteins. Examples of these include enzymes, some hormones, and hemoglobin. Disruption of the hydrogen bond of functional protein leads to their denaturation, and inactivation. Enzymes increase the rate of chemical reactions by combining specifically with the reactants and holding them in the proper position to interact. They do not become part of the product. Many enzymes are produced in an inactive form and are inactivated immediately after use. Nucleic acids include deoxyribonucleic acid, DNA, and ribonucleic acid, RNA. The building unit of nucleic acid is a nucleotide. Each nucleotide consists of a nitrogen-containing base, a sugar, ribose or deoxyribose, and a phosphate group. DNA, the stuff of genes, maintains genetic heritage by replicating itself before cell division and specifying protein structure. RNA acts in protein synthesis to ensure that instructions of the DNA are executed. ATP, adenosine triphosphate, is the universal energy compound used by all cells of the body. When energy is liberated by the oxidation of the glucose, some of that energy is captured in high-energy phosphate bonds of ATP molecules and stored for later use. And now it is the review questions on page 59, and I will not be reading those. And that concludes Chapter 2. Thank you.